All right, thank you, Jamie. Can everybody hear me all right in virtual space and in the room? Excellent. As Jamie mentioned, I'll be continuing our theme of tutorials for using HTCondor to run computational work, and I'll be talking specifically about Condor's built-in workflow management tool called DAGMan. There we go. And what's covered in this tutorial is, first off, why would you create a workflow? How to describe workflows as directed acyclic graphs, or DAGs, which is where HTCondor's DAGMan DAG Manager gets its namesake. So we'll talk about how to execute a workflow using DAGMan. I'll talk about node level options, so options that let you modify aspects of the execution of certain jobs within an overall workflow, modular organization of DAG components. And I'm really just going to introduce some of the most popular and most important features that we see researchers and other Condor users implementing. There are some extra slides at the end of this presentation and quite a bit more information about DAGMan in the Condor manual. But you can learn more about DAG-level control and additional DAGMan features in slides that I won't cover today, but that are in this presentation toward the end. So first off, why would you want to run a workflow? And the short answer is automation. Generally, workflows or workflow is a term used to describe a set of tasks, whether they be computational or otherwise, that need to be executed in a particular order, and where there are often sort of rules or guidelines about what order they're executed in and when certain types of tasks can be executed at the same time. So our objective with computing is to submit jobs in a particular order automatically when we're talking about using a scheduler like HTCondor, so that we don't have to manually submit some jobs, wait for them to finish before submitting others ourselves. And this is especially useful if we want to reproduce the same workflow multiple times. With any workflow tool, not just Condor's built-in DAGMan tool, one of the great benefits is that you can effectively codify, record the work that you're doing, and that these workflows can be handed off to perhaps another user who could then modify, adjust, or implement them for their own work too. And these are all things that are excellent and important for research, computing, and science. And we call Condor's workflow manager tool a DAG manager, or DAGMan, partially because of a mathematical term describing the type of workflow that we're often talking about with computing in a directed acyclic graph. And there's a diagram here on the right from the Wikipedia entry for directed acyclic graph. So I assure you this term originates well outside of the context of computation and Condor. But it refers to a topological ordering of vertices or nodes that is established by directional connections or edges. So these are the terminologies regularly assigned to the concept of a DAG. The acyclic aspect refers to the fact that a directed acyclic graph has a specific start and end point. And even in workflows in Condor's DAGMan, while we can have cyclic subcomponents, there needs to be a defined start and end. So those are sort of where the terms directed and acyclic come from. It needs to be directional. With the computing workload, we want a defined start and end. We don't want something that's going to continue unchecked in a cyclic, never-ending manner. We want it to end or choose to exit at some point, even if we need some components to be iterated over or cyclically repeated. And we'll talk a little bit about exactly how you can achieve that sort of repetition in DAGs within Condor. So Condor has a DAG manager, we call it DAGMan, and there's a specific part of the user's manual that's all about DAGMan workflows. It's part of the manual that reads a little bit more like kind of a how-to step-by-step conceptual introduction versus just being a reference. So I really recommend looking at that. And in order to introduce some of the most common and important features in DAGMan, we'll start with an example workflow that's kind of a common high-throughput computing scenario, where we might imagine that our first job will take some large set of input data, split it up into pieces. Then we might have n number of jobs that analyze those n pieces and combine the results. In DAG terminology, we will refer to the different jobs as nodes, and you'll hear me refer to that terminology just like it applies generally to the concept of directed acyclic graphs. And then we'll express the edges in a very specific way to HTCondor, that establishes the order of tasks as they should be executed, submitted on your behalf by DAGMan, as you've got them set up as individual jobs. And we'll simplify this example just for the sake of simplicity in the example DAG files and submit files that I'll show you. So we'll refer to that first task as A, those middle tasks as B1 through Bn, and I'll frequently just show 3 of them for simplicity, but you could imagine that any of the B nodes in my example DAGs through this tutorial could go all the way to Bn, some n number of jobs there in that middle step, and then a C job. And the DAG input file is going to communicate the nodes and directional edges of our workflow. And so here's what the DAG file, which is different from a submit file, would look like for this simple workflow example. We have a job A defined by a node name A, and then a submit file associated with that we, the user, are supposed to create, but that otherwise Condor will submit on our behalf when we submit this overall DAG. We've got jobs B1, B2, B3, job nodes B1 through B3, and again, those could be through Bn. Job C, each of these has their own submit file. And then we establish the edges with these parent-child statements. So we say that A is a parent to children B1 through Bn, and B1 through Bn are parents to child C. And just with this set of information and the submit files, Condor's DAGMan, once we submit this DAG file, will know to execute these jobs in that order, where it would only submit the B jobs after it has completed the A job, and the C job after the B jobs have been completed. The node names are used by various features that we'll show you throughout this presentation, so that you can modify aspects of their execution, implement retries, those sorts of things. And you get to decide what the node names are. So the node names and the file names are completely up to you. You don't even have to call it .dag, that's just a convention. You've seen submit files referred to as .sub, that's also convention, mainly to make them human recognizable. But otherwise, all of this is up to you. The node name and the submit file name don't have to match, but I will have them match in these examples just for simplicity, so it's really clear to you which job nodes correspond to which submit files. And in our DAG directory on the right here, you'll see the various files that we should expect to have already created in order to submit this DAG. So the DAG file, all of the submit files that we named within the DAG file, and all other job files as you've seen in the previous presentation. So including our input, we'll have, as with any other jobs, we'll have output, error, and log files coming back for each job. I'm not going to show most of those since we've already established how they appear and what they look like. We'll be focusing specifically on showing you files that are more specific to the DAG themselves. And with that simple definition of nodes and parent-child relationships, you can achieve really endless workflow shapes. These are just a few. In fact, the ones on the right are from a different workflow tool that works with Condor called Pegasus. And the one on the far right is a bioinformatics pipeline, where you can even see there's sort of a shish kebab structure of repeating elements. We'll talk about how to establish repeating elements so that it's easier to define those in a DAG later on. And DAGs are also useful for non-sequential workloads. So something that you might not think of as a workflow with sequential steps. Examples being just a set of HTC jobs. You've already seen excellent examples of how to communicate a large number of jobs with a single submit file. There are some features of automation and robustness that appear in DAGMan that just aren't quite as available or useful in a submit file only context. And so you can always have a set of HTC jobs expressed in a DAG with no parent-child relationships. And you can combine multiple workflows rather than having to write DAG files for each of several disjointed workflows. You can still have one big DAG file and just establish which nodes are connected to each other or not based upon their parent-child relationships. So let's go back to our basic DAG input file. We've got our job nodes and our parent-child edges communicated. And let's look at what it looks like to submit and monitor this DAG in the queue, and what actions Condor and DAGMan are taking on our behalf to manage our workflow for us. Ooh, there we go. So first, to submit a DAG to the queue, there is a different submit command. So for regular submission of a submit file, it would be condor_submit. For submitting a DAG, it's condor_submit_DAG, and then you give the DAG file name. And that tells Condor that you're passing it a different differently formatted file in the format of our DAG file with job nodes and parent-child relationships communicated. And what Condor spits back to us after that is a list of different files that it will create that will do some logging. We'll talk about those a little bit more after I walk you through what it looks like in the queue. But you'll notice that it says one job was submitted to cluster and then gives the cluster number. That actually refers to a DAGMan job that will be running in the queue on our behalf to submit all of our other jobs for us. And that's why it says only one job, even though our DAG, of course, in our simple example has 5 jobs. So if we ran Condor Q, what we would see at first in the default batched output is shown here. If you run this right after you've submitted, right before the DAG process has started submitting other jobs on your behalf, you'll notice that interestingly, it'll say that there is one job in the queue, but there are no numbers listed yet for the number done, run, idle, or total. And that's because the queue does something a little smart for us when it knows that we're running a DAG workflow. If we run the no batch, this is where you can see that there is in fact a job submitted to the queue called Condor DAGMan. This is the DAGMan process. It runs on the access point in the queue, and it has a cluster and proc ID number for the job ID. And we've caught it here within just the first several seconds when our DAG is initializing. But pretty soon it's going to start submitting jobs on our behalf, and it really is within seconds. So seconds later, node A is submitted because we've just got that one node A job that is a parent to our B jobs. And so now we can see DAGMan has finished initializing. The queue is smartly telling us that there are 5 jobs in this workflow, and it batches all of those together, just like it would jobs all submitted from the same submit file in a cluster. But they're each going to have different cluster numbers. These are separate jobs, separate submit files that will end up in the queue. So our job A has a cluster ID of 129. When we run Condor Q at the no batch output, we see both that DAGMan job and our A job, which I told you before in this example, we could think of as being sort of like a data split task. So that job will go from idle to running to complete. Once it's complete, and to the extent that it appears to have been successful by having a 0 exit code for DAGMan, our DAGMan task will then submit our 3 B jobs. And again, we're getting smart totals here, still 5 total jobs. There's the 1 done that's referring to our A job, 3 idle referring to our B jobs that we can now see in the no batched output, each with their own separate cluster number, separate job ID in the queue. And after jobs B1 through 3 have run, completed, and exited the queue, job node C gets submitted on our behalf. So we have 4 jobs done, including our A and B jobs, 1 idle for our C job, and it will run and complete. When it completes and leaves the queue, DAGMan will assess that it has completed the work of the workflow as far as it can go, and will remove itself from the queue. And so then the queue will be empty. And so you're lucky, again, there might be seconds where the DAGMan job exists by itself after our C job has left the queue. So let's talk about what files are produced. At the time of DAG submission, there are a handful of files that are created. One of them, this mydag.dagman.out, so it's going to be named .dagman.out based upon the name of our DAG file, will have detailed logging about every action that DAGMan is taking in deciding which jobs to submit, when they got submitted, and what's happening with them along the way. Because that DAGMan job is a job running in the queue, though it's running on the access point instead of out on an execute point, it also has a submit file and a log file that got created on our behalf when Condor submitted a job just to be our DAGMan task. We didn't have to create that submit file. It gets created on your behalf based upon submitting the DAG file. There are error and out files associated with that Condor DAGMan job, standard error and standard out. And then there's a combined log of all of the log messages from all of our jobs. So even though each of our submit files might have specified a log file with the typical information we expect in a Condor log about when each was submitted, when it started transferring files, when it executed, et cetera, there's this combined log for all jobs that you could mine later if you wanted to. And then once a DAG completes, all of those other files are printed to, finished up, but we get a new file called our DAG file.dagman.metrics that gives us metrics about how many jobs within the workflow ran and succeeded. So you can look at that too just to see and make sure that your workflow is run appropriately. You can remove a DAG from the queue. So if you know that there's something wrong with your workflow and you need to fix it, you can Condor remove the job ID associated with the Condor DAGMan job itself, which will remove any of the other workflow jobs that are still queued and then remove itself. It will create a rescue file such that after you fix things, you could resubmit that workflow, and only the node jobs that had failed, had not successfully exited with a 0 exit code, only those would be resubmitted to run. There's more about the rescue file. You can get rid of it. You can overwrite it if you want to start the workflow fresh. But there's another slide at the end of this presentation and more information in the manual about the rescue file itself. What happens if things fail? Let's say that in our simple workflow, one of our B jobs, B2, failed. DAGMan will continue to run any other node jobs. Those are handled separately. Any other node jobs that it can run that are not a child of the failed node, it will continue to run. But as in the example at right, if B2 fails, the DAG would fail and exit after all of the other B jobs have finished, but it would not proceed with job node C, because that would have depended on our failed B2 node succeeding. And this brings up one of our important best practices when using workflows. We've shown you wonderful ways to submit multiple jobs with a single submit file in the previous presentations. But when you're developing a workflow, the whole point of having separate job nodes is to have individual control of those components. And so it's actually a not best practice to submit multiple job processes per submit file. It's the best practice to submit a single job process per submit file. And then we'll show you some examples later about how to sort of modularize that so that you actually can have reusable submit files rather than having to have actually a separate submit file per job. But basically, otherwise, if any single job process inside of a node, so any single job process of a submit file fails, that whole node is considered a failure by DAGMan, rightfully. But it actually gives up on that whole node, removes the other jobs. So even though it would have continued running our B1, B3 through N jobs, if something in B2 failed, if B2 had only one process out of many failed, all of those jobs would be removed by the DAG because it's assuming that it should just give up on any of those jobs that were submitted with the same submit file. And similarly, when we talk about retries later, retry of a job node resubmits the entire submit file rather than just one of those jobs. What about if jobs are held? So let's say that there's something wrong with our B jobs, they all get held. What's really lovely here is that because each of these jobs has its own submit file, has its own job cluster in the queue, we have a lot of control here, and we can intervene as a user without having to sort of remove or interrupt the whole workflow. For example, if these jobs were held and we want to Condor queue edit them to fix whatever was wrong, like request more memory or correct a typo in one of the files that was supposed to be transferred, we can make that fix and then release those jobs to rerun, and the whole workflow just continues on. Basically, the DAGMan job detects that those jobs continued to run and eventually succeeded, and it continues on its way as if the hold never happened. You can also remove the entire DAG, fix the problem, and because of that rescue file, resubmit the DAG with the same Condor submit DAG command, and it will pick up where it left off, only rerunning any jobs that hadn't already successfully completed. All right, so there's some sort of basics of troubleshooting. There's a little bit more in the Condor manual. Let's talk about node level modifiers. I already mentioned retries, for example, that you might want to retry a node. We'll talk about some of those features in this next section. So first, by default, job files are found relative to the DAG submission directory. So what if you wanted to organize your data differently, just like we've shown you in previous presentations? Well, one of the first modifiers that we'll introduce here is the dir modifier. With the dir modifier, you can set a different directory from which DAGMan should expect to find the submit file, and therefore all other files listed in the submit file for that job node. So for example, on the right, in our DAG directory, we could, instead of having all of our submit files up at the top of the DAG directory, we could have each of those in a separate, say, A, B, C folder, along with all of our other job files as specified in the submit file. But this way, the DAG knows to find our submit file within these other directory locations rather than at the same directory location as where we typed Condor submit DAG. Each node also includes the ability to add pre and post scripts. These would be lightweight tasks that we might need to only run on the access point. Basically, we want any heavy work that can run on an execute point to be part of the job. But in some cases, there may be tasks of like reorganizing data after one job node before another job node, something like that. So in our split example, where A is a job that's splitting files, maybe we want a PostScript that has to run on the access point to sort those files into different folders for our B jobs. Or similarly, before we do C, we might want a prescript that has to run on the access point that creates like a single tarball of all of their outputs, all of the B outputs, so that they can be processed by the C job. So this is how you would specify that in the submit file. And there's a little bit more information again on pre and post scripts, both at the end of this presentation and in the manual. I mentioned that you can retry job nodes. And this is most useful frequently, not just for retrying under a failure condition, but for achieving some aspect of cyclical execution, where maybe you want to iterate, run the same type of job for so many different iterations, accumulating output. So rather than having to write lots and lots of parent-child statements to repeat that task over and over again, you can program a retry. And so here's how you would specify that, indicating just like our other DAG or our node level modifiers, the option, the name of the node to apply it to, and in this case, 5 says retry that node up to 5 times. I mentioned there are a couple of other bits about retries. You can also pair a retry with a postscript so that you've got a postscript that runs on the access point that maybe looks at your output and decides if another iteration is necessary or if there was a true failure. So that's one way to get around, if your job node doesn't always exit 0, even if it's successful, or if you want to decide whether to iterate again. And just a side note, if you need to retry just upon failures, the max retries option in the submit file is preferable because that's the simplest level of retry that retries with the same job ID rather than resubmitting. So it's a little more lightweight, and it accommodates the situation of multiple job processes per a single submit file. Again, though that's not a best practice, max retries would apply then only to each individual process rather than to the whole job node. Can we hold questions until the end?
A quick comment here. The failure is defined by the postscript. So there is a lot of power in controlling when a job fails in the postscript.
Yep, I'll repeat what Marone just said in the room. And this is in one of the later slides about postscripts and retries. When you use a postscript or a prescript, that is defined as being part of the node. And so a postscript failure is interpreted to mean that the node has failed, which is part of how you can achieve this retry and iterations.
Yeah, but let me be precise here. The postscript may not fail, but it may decide that the job failed.
Yes.
And throw the flag that will trigger a re-execution, and even more than that, in principle, the postscript can queue edit the job submit file, modify it, and cause it to rerun. So you can make the postscript as smart as you want in the case of failure of the execution of the job.
Thank you. All right, the last little bit here before we wrap up, I'll talk about modular organization and control of DAG components. What this really gets you is not just sort of added robustness and repeatability within your DAG, but ease of communicating repeatable components or substructures within your workflow so that you don't have to recreate each of those explicitly in the production of your DAG file. So as an example, here's a workflow from LIGO. It's kind of old at this point. I don't even know if they're using it anymore. But you can see that from left to right, there are sort of repeating substructures within this overall DAG. And so I'll show you some ways. There are more details at the end of the presentation and in the manual for how to achieve these sort of repeating components. And the first one I'll show you is really useful for the best practice of having only one job process per submit file, But then you're asking, so now I have to write a separate submit file for every single one of my jobs in that B section, even if there's a million of them. And the answer is you really don't if you use the VARS option. This is a node level modifier that gives you repeatability and the ability to use a submit file on repeat. So for all of our B jobs, right, they're probably all doing, using the exact same executable, just different input files. We can, in the submit file, insert variables here that will be populated from input in the DAG file. So we still queue just one job process in that submit file. But you'll see over in the DAG file, in addition to defining each of our B1, B2, B3 jobs with that single submit file, we can populate the values for the data and opt variables that we've defined in the submit file. So now we have one submit file that could be used for n number of B jobs just by building in these VARS statements into our DAG file. To achieve sort of repeating substructures in your DAG, or even just to sort of break up your DAG file into simple components and to make it more simple to express, you can use the SPLICE feature. And so in this example, rather than defining all of jobs B1, B2, through N, and then also listing them out in the parent-child statements, we can instead make a SPLICE listing our B jobs that when we submit the overall DAG file, gets read in as if that was one big DAG file. So DAGMan reads this in as if it's one big DAG file, but for us, the human, what we've done is made it a lot simpler to grasp what's going on with this workflow by just having parent A, child B, parent B, child C, and that B child actually referring to the SPLICE that includes all of our B1 through Bn jobs. And this is also how you could have sort of copy paste. You could use the same SPLICE to have repeating components. There's a slide at the end that gives a specific example about that. What if some DAG components can't be known ahead of time? So kind of maybe a weakness of the DAG file is that you have to explicitly state everything at the get-go. But what if, for example, when our A job splits up a bunch of big input, each to be separate input files to our B jobs, we don't know until that split has happened how many pieces are going to be necessary. So we don't know the value of N. We don't know how many submit files. We don't know how many B job nodes we need. And the answer to that is to use a sub-DAG. This is a bit different from a SPLICE, even though it will kind of look the same in contents for the sake of these examples. But in this case, a sub-DAG is another DAG that will get submitted by our outer DAG. It will be another job in the queue, another workflow managing its own combination of jobs within the sub-DAG file. So that's part of why I've named it b.dag with that .dag convention rather than .splice. But in this case, when we submit the outer DAG file, which is all we have to do, the outer DAG won't go and read that inner DAG file, and it won't use it to populate its picture of the overall workflow. It just knows when I get to B, I have to go submit that as a DAG rather than as a submit file. And so our job A could split up our input, write the submit files for all of our B job nodes, write the B sub-DAG file, and then only when our outer DAG gets to the point of needing to submit that B component will it submit that as a separate DAG for us. This is also how you can achieve cyclic iteration of a substructure of your workflow, not just a single node, by putting a postscript and a retry on that B component. These sub-DAGs are treated like another node in the overall outer workflow. And so they can have a postscript and a retry. And just like Rowan and I were mentioning before, that postscript can do some smart things to evaluate what happened after that B sub-DAG ran the first time, modify some files, trigger the retry by giving a false failure of that script, and trigger that whole subcomponent of the workflow to run again. My time is up, and there's a lot more at the end of this presentation and in the Condor manual, especially sort of expanding on some of these features I've introduced. Those things include more node level options, modular organization of DAG components, DAG level controls, so that you can implement things like throttling how many total jobs DAGMan should ever have submitted to the queue at once, and some other DAGMan features that are really useful. And with that, I'll take some questions. Thank you.